Calculating limits using limit laws. There are some properties that we are going to be using this year with the limits, and the precursor to using these properties is to identify that the functions involved inside whatever operation is going on exist and are real, however many you might have. First rule is the sum rule, which basically says that the limit of two functions being added together is the same as the limit of each one individually and then added together. For either case, you would take L plus M to get your final answer. The difference rule is the limit of a difference is the same as doing each one individually and then subtracting them. So for this, we would take L minus M. The product rule is simply the limits of each individually multiplied together. And the quotient rule, you're dividing. The only thing to be watchful of is that M, the denominator, doesn't go to 0. The constant multiple rule says that if I have just a number factor in front of any function, that number constant carries over to the limit by multiplication. How we can use them. Some of these are going to be done now and some of them will be done in school. The limit as x goes to negative infinity of function g. Notice I have two functions here, a piecewise function that's graphed and a piecewise function that's presented analytically. If I am heading to negative infinity, that means graphically what's going on way over on the left of the graph. What's happening way over to the left is going to correspond to, on function g, looking for the appropriate signage on the piecewise function, which negative infinity would be this piece right here. So I'm going to use this function and say I'm analyzing the constant 4 plus 12 being divided by x values that are getting bigger and bigger in a negative fashion. If I take 12 divided by negative 10, 12 divided by negative 100, 12 divided by negative 1000, this piece goes to 0, so the limit answer is just that constant of 4. The next one is looking at function g, and what's happening as we approach negative 6. Notice no symbolism here, so that means you're coming from the right and the left. We have to check both sides. If I take the limit as x approaches negative 6 from the left of g, then that piece means I'm looking at the top. That would be less than or equal to negative 6. So it would be 4 plus 12 divided by negative 6. We end up with 4 take away 2, which is 2. Coming from the right, the limit as x approaches negative 6 from the right of g. Right of g means you're working with this piece right here. So I'm going to take 1/2 of negative 6 plus 5 to get me negative 3 plus 5, which is 2. Since both sides of negative 6 are heading towards a value of 2, that means that this limit exists and its answer is 2. Number 6 is the sum, and this is our first rule. I'm going to look at each piece from each function and then add them together. Negative 6 from the left on function f. Here's negative 6. Go to the left, jump onto the curve, follow it towards that value. I am approaching a value of negative 1. I'm going to go to g. I've already done that piece. That one goes to 2. Total in this case is 1. Number 7, x is approaching 0 on the graph of G. Back up to G. It's 0 is where we have a cutoff. I have to do both sides. The limit as x approaches 0 from the left on function G. That would be this first piece here. So I'm working with 1/2 times 0 plus 5, which is 5. Coming from the right-hand side, the limit as x approaches 0 from the right of function G. I am using the square root function. So I'm going to take the square root of 0, which is 0. Notice the two sides are going to two very different heights. They are not coming to the same height. Therefore, this limit does not exist. You can't be in two different places for the same x value. The next one is going to involve subtraction and a constant multiple. So I'm looking at function f, the graph, at -8, making sure to check both sides because there's no plus or minus. So if I look, -8, there's 5, 6, 7, 8, is right here. The -10 is mismarked. It should be right there, so be careful of that. It smushed it over. So 5, 6, 7, 8. Both sides look here like they're coming towards 0. So that piece goes to 0. -2 times, and then we're looking at g of x now for -8. That means I'm going back up to the interval that contains -8, which is this piece. So I'm going to say 4 plus 12 divided by my -8. When I work this out, I'm getting -8 plus 24/8. And then when I go further, I'm going to say this is -64/8 plus 24/8 to get me a total of -40/8, which gets me -5. Limits analytically. What happens for limits analytically is we have some different approaches. The first is direct substitution. If you can plug in the number a and you get a value for your limit, you're good to go. If I have an indeterminate form, that means you're plugging in and you get a 0/0. Then we have to go back to pre-calc and algebra 2 and use all of our skills to figure out how to manipulate these expressions to then be able to plug in. Or an indeterminate form of 0/0 can't be manipulated algebraically, so we're going to take on a graphical or tabular analysis to identify the patterns. The first one, our technique is always to try to plug in. So I'm going to plug in that 4 to make it 25 in the bottom. Now I'm analyzing 1/25 to the 3/2. Going back to pre-calc, the 2 in the denominator means I'm square rooting, which would get me 1/5. And then 1/5 being raised to the 3rd power gets me 1/125 for that limit. The next one is the greatest integer function. So you have to remember your steps on the greatest integer function. So very quickly they look like this, and then you make the jump to the next integer, and so on and so on. That's your greatest integer function. I always call it the round down function because if I am here from 0 up until 1, any of those values that are a little bit greater than 0 round down to 0. Then when you jump to 1, and anything past it up to 1.999 is still here at this step of 1. So anything from 1 to 1.9999 infinite times would round down to 1. So when I'm looking at plugging in -3/2, I'm going to round down and I get -2 for my answer. Pre-calc skills, I'm going to plug in the 3 pi over 2 into the cosine graph. So then I'm looking at e to the cosine of 3 pi over 2. That value is 0. So e to the 0 then becomes 1. Again, e, but to the natural log of sine of pi over 4. Memory recall with pre-calc reminds me that the sine of pi over 4 is either 1 over root 2 or root 2 over 2. Either is valid. And then again, using my pre-calc skills, e to the ln are inverses, so I'm back with just the exponent of 1 over root 2. The next one, I plug in and I get the indeterminate form of 0 over 0. This is where those pre-calc skills are going to come in very handy. I'm going to expand out my binomial. So I'm going to get 9 plus 6x plus x squared minus 9 all over x. Notice I carried down the limit notation because I'm not evaluating, I'm just changing its form. That's very important in math communication. I'm bringing down the limit again, necessary to bring it down until you evaluate. The 9's cancel each other out, so those are gone. Factor out an x, I'm left with 6 plus x over x. Now I can cancel the x's to be left with just this expression as x approaches 0 of the quantity 6 plus x. And that will just become 6 when you plug in 0. Okay. Going back to pre-calc, what's going on is that this graph is going to have a hole at 0, remembering the differences between when you have holes versus when you have asymptotes. So start thinking about that. And then I'm looking now for this end answer. This end answer is the height of the hole in the graph at 0. 17 is also an indeterminate form when you plug in -2. So algebraically, I'm going to say the limit as x approaches -2 of, factoring it down to x minus 7, x plus 2. Denominator, 2x, x plus 2. Again, canceling those out, indicating a hole in the graph, and our job now is going to be to find the height of that hole. I will plug in the -2 to get -9 divided by -4. Height of the hole is at 9/4. 18, another indeterminate form, but dealing with fractions. So the manipulation for this one, there's multiple representations. I'm going to give you one. I'm going to look for a common denominator. My common denominator is 4 times 4 plus x. Then in the numerator, I have to change each one. This one goes to a 4 minus the quantity of 4 plus x. Technically, this is all divided by x, but if I think back to rules from algebra, I can multiply dividing by x as multiplying by its reciprocal 1 over x. Then, again, limit notation is still here because I'm still rewriting my expressions. The 4 take away 4, gone. That negative applied to the x makes it a -x over 4 times 4 plus x. Carry down the 1 over x. I can see the factor of x to cancel. Cancel those out. I'm left with -1 divided by, plugging in the 0, and I have 16. That's the height of the hole. Number 20, how do I break down larger degree polynomials? One of the ways is factoring by grouping, which is not working here. And the other way to break down a polynomial from memory recall is to use a technique called synthetic division. So I'm going to take my factor of -4 here, because when I plugged in -4, I did get 0 divided by 0. So I know then it's that indeterminate form, and I have to break it down. I take my coefficients, 1, -4, -25, and 28. And I go through the process of synthetic division. Bring down the 1, multiply by -4, combine to make -8, multiply to make 32, drop down that column, you get 7. Then we get -28, which is ideal because we don't want to have a remainder of 0. If you have anything other than a remainder of 0, that means the original polynomial didn't factor. So now I'm going to take the limit as x approaches -4 from the right, and I'm going to rewrite it as the two binomials that multiply to this cubic. Since I divided by -4, one factor is x plus 4. That accounts for the divisor. What was left, the dividend, is what I'm writing now. So I have x squared minus 8x plus 7. The bottom, I'm going to factor out an x. I still have x plus 4. Common factor of x plus 4 is canceling. And then I can plug in my -4. So I have 16 plus 32 plus 7 being divided by that -4. So we end up with -55/4 for the height of the hole in that function. And that's our limit value. Last one is I'm looking at a piecewise function, and I have to find the value of b such that the limit at 3 is going to exist. In order for the limit to exist at 3, that means both of these sides have to converge to the same value. If they have to converge to the same value, I set the two expressions equal to each other as my first step. So then I know I'm targeting that same height. I want to target that same height at a value of 3. So I plug in, left side is 9 minus 1, right side is 6b. Simply solving for b, we end up with 8/6 or 4/3. That's the value of b such that the limit exists.